some application of these exponential logarithmic models. So today you'll recognize some of the five most common types. You'll use them to solve real world problems. So here's exponential growth model here. You put money into a mutual fund, or you buy something that appreciates, or like a house, whatever it is. As time goes by, that amount of money will grow exponentially. Okay, so you buy a car which depreciates, then over time that money is going to depreciate exponentially. Or carbon dating goes down exponentially as time goes on. The amount of carbon in an element goes down. The Gaussian model here's an oversimplification of it, but it's a bell-shaped curve, and it's great for statistics, because when people do something like take a test, right, there's going to be an average score on a test, right? So this is the distribution on the y-axis, and this is the score of the test. There will be a score which will have the most distribution, that score will show up the most from students. That's the average score right there. Okay, logistic growth, like I said, is great for population, because like bacteria will grow in a petri dish exponentially at first, right here, but eventually they reach the limit to growth because they're confined by their environment. They run out of resources. Okay, there's not enough space, or food. In this case, logarithmic model, this would be great for the Richter scale or for pH scale, like I said, in chemistry. So let's try an example then. This are estimates of the amounts of billions of dollars spent on advertising through 2007 to 2011. Okay, this is a scatter plot shown, and it's an exponential growth model, which we've modeled here for you. Okay, and where S is the amount of spending and T is 2007. So it is growing exponentially. It doesn't really look like it, but it is growing exponentially right there. So it's a slow growth. But so let's compare the values given by the model with the estimates shown in the table. According to this model, when will the amount of U.S. online advertising spending reach 40 billion? So what we're trying to look at here is when will this spending reach 40 billion up here? It should be somewhere around here, around 12 or 13. But we want to know when will that happen. Well, what we'll do is we'll plug in the spending of 40 billion, and we'll solve for time right here. To solve this for t, first I'm going to divide by 10.33, both sides. Gives me about 3.9-ish, and that equals e to the 0.1022t. Now I'll take the natural log of both sides, because that'll get rid of this. I can bring the exponent down. So I'll have the natural log of 3.9-ish. I don't have that rounded in my calculator yet. Equals 0.1022t. And I'll divide both sides by this 0.1022. 0.1022. And that gives me, actually I'll just pull up the calculator and show you. So it'd be 40 divided by the 10.33. That's how we got this value to 3.9. I want the natural log of that, so I won't round it. I'll just grab it here. Hit enter on that. That's this value. And then I'll divide it by 0.1022. And that gives me the answer, which is about after 13.2 years. So the time would be 13.2 years. And that was the number of years since 2007. So really I should round up to 14 years. And so after 2007, add 14 to that, it'd be 2021 was when we'd finally spend $40 billion on advertising. Actually, they said t equals 7 was 2007, so really this was t equals 14. Should have been 2014. That should be our answer for when we'll reach 40 billion in sales, or in spending. Okay. So let's look at the next example. Then let's look at carbon dating. In organic material, the ratio of the number of radioactive carbon isotopes, carbon-14, to the number of non-radioactive carbon isotopes is about 1 to 10 to the 12th. Okay? And basically when a material dies that involves carbon, the carbon-12 content stays the same, whereas the radioactive carbon-14 decays. And it has a half-life of 5,700 years. So we can use that along with this formula to date things. Okay, this is how anything that has carbon in it. This is how scientists have dated how old the Earth is, that the Earth is 4.5 billion years old. This is one of the ways that they've dated that. Okay, so here's you can see as time goes on, the amount of carbon-14 remaining decreases, okay, exponentially. So it's a handy equation for dating anything with carbon in it. Okay, a Gaussian model then, like I said, is used in statistics for normal distribution. It's a bell-shaped curve, okay? Here is, for standard normal distributions, this is the model we use, okay? The average value can be found from the maximum on the bell-shaped curve. So you can either graph the function and find the maximum. That's probably going to be the easiest way for us to do problems like that. So let's do an example then of that. The SAT math scores for college-bound seniors follow this formula, okay? Let's sketch a graph of this function, and then from the graph, let's estimate the average ACT score. So let me pull this over. It says x goes from 200 to 800, so let's try to use that information as well. But here's the function. Let's pull out a calculator and plug this in. I'll plug it in. I'll pause it and plug it in. All right, so once you get it typed in, it's pretty tough to type it in. And then the graph, it's really tough too because you have to change your window. I had to mess with my window for a little while, but they told me to go up, it was from 200 to 800 for SAT score, so I went from -10 to 1,000 just so I could see the axes, but 200 to 800 is fine. And then my Y max actually, this is a distribution. It ends up being really small, 0.005 is what I typed in. When you go to graph, then you can see the bell-shaped curve. And it wants us from this to find the average SAT score. So let's do second calculate maximum, 4, and hit enter, enter, enter. And the average SAT score was 515. Let's write that down. Average SAT score was 515 from that graph. Okay, we can look at that graph on here as well. You can see here's the distribution, and then the average SAT score was 515. Okay, in 2008. All right, let's look at logistic growth now. Some populations initially grow, like I said, exponentially. Then after a while, they run out of resources, run out of space, whatever it is, food, and then they reach a limit to growth. Okay, so this looks complicated, but this is our logistic growth model. Let's look at this specific one. It says on a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the flu is modeled by this function. So over time, it grows exponentially. Eventually, it reaches a limit as more people get it. There's only so many people to infect. Where Y is the total number of students infected after T days. The college will cancel classes when 40% or more of the students are affected. Let's answer these questions then. First, how many students are affected after 5 days? Okay. So after 5 days, T is the total number of students, or Y is the total number of students affected, and T is the days. So we're going to plug in T equals 5 for the first one in right here, and let's find out what we get for Y. And then the next question is, after how many days will the college classes be canceled? Let's do this. Obviously, you can plug in 5 in your calculator, and you could enter this in. Okay. And then for the next question, the college classes are canceled when 40% or more of the students are affected. So the total number of students, the limit to growth is at top. So the total number of students must be 5,000. So 40% of 5,000 would be 2,000. So after basically we get 2,000 people infected, then school's going to shut down. So we want to answer this question for part B. When do we get 2,000? For this equation. So we want to solve this equation for T, which is a little bit tricky to solve algebraically, but it's good practice, so we're going to go ahead and try it. So first, let's plug in 5 for T here. Let's plug that into the calculator. I'll show you what you get when you plug that in. Okay, I think I plugged it in right, hit enter, and you get 54. So it looks like 54 students are affected after 5 days. Okay, that's part A. Part B now, we're going to solve for t in this equation. So let's cross multiply, in which case we get 2,000 times this quantity, 1 plus 4,999 e to the negative 0.8t equals 5,000. Okay, let's divide both sides by 2,000. We get this. Okay, I can drop the parentheses now. Let's also subtract 1 from both sides now. Get rid of that. Let's then divide both sides by 4,999. Okay, it gets rid of that. And then let's take the natural log of both sides, get rid of the e. Okay, that gets rid of the e. Then I have 0.8t. Let's divide both sides by negative 0.8. That gives me just t. I'm going to divide both sides by negative 0.8 now. And that should give me my answer for t. So this is what I want to do with my calculator. Let me pull that up and show you what you type in for that. It'd be natural log of a big fraction, a couple big fractions. Let me see, how much time do we have? We got time, I think. So let's type that in. So I'd have, this is my fraction. I need another fraction, so let me do alpha y equals another fraction again. So we got 5,000 over 2,000. Whoops, need another 0 on the top. Minus 1 all over 4,999. And then that's all going to be divided by, so I'll hit enter on that, that gives me the numerator. It's all going to be divided by the negative 0.8, which gives me about 10.1. So about after 11 days, I'd have to say, I have to round up. So t equals 10.1 here. So after 11 days, the school would have to cancel. It would have to cancel on the 10th day, I guess, before you reach the 2,000. So 10th or 11th day for there is when the school's going to want to shut down, because 40% of the students will be affected. All right, let's try one last problem involving the Richter scale. Here's the Richter scale formula. The Richter scale, the magnitude R of an earthquake is given by the log of the intensity I over initial intensity, where I sub 0 is minimum intensity of 1. Okay. So let's look at a couple earthquakes. First, the one in Nevada in 2008. It had a Richter scale of 6. Let's find out what the energy intensity of that would be. So what we could do is plug in 6 for R. Okay, and that's equal to then log of I, which is the energy intensity, over the initial energy intensity, or the minimum, which is 1. We're going to solve this equation for I right here, and that'll give us the actual intensity of that earthquake. So I'm going to change this into exponential form. I'm going to do base to the exponent, so I'll do 10 to the 6th equals I over 1, because that's how you go from log to exponential. You do base to the exponent equals the argument. So it'd be 10 to the 6th equals I over 1. Sorry, I over 1. I don't need the 1, so basically my energy intensity is 1 million. 6 decimal places for part A. So basically the one in Nevada in 2008 was about 1 million for energy intensity. Let's look at the one in China in 2008. It had a Richter scale, it was an earthquake of about almost 8 on the Richter scale. So 7.9 equals log of I over 1. Now if I change it to log or exponential form, I have base to the exponent equals the argument. So it'd be 10 to the 7.9, which we look at that strength, that would be about 79,432,823. So you can see that this one's almost 80 million times stronger, okay, the one in China. So you can see how this formula helps us then to evaluate, how strong these earthquakes really are. It's a useful formula because, these numbers are harder to look at. Oh, this earthquake, was 1 million times strong. This one was 80 million times strong. These numbers are a little more easy to communicate, I guess, to the general public. That one had a Richter scale of 6 or 8. Okay, but keep in mind it's a logarithmic scale, and 2 points on the Richter scale equates to obviously much more energy. Okay. All right, I hope this helps.